Before we begin, please note the following. This presentation was produced with the assistance of artificial intelligence, including narration, data analysis, visuals, and design elements. While every effort has been made to ensure accuracy, AI-assisted workflows may introduce errors. Viewers are encouraged to verify claims independently. The findings presented here reflect what the data and source material indicate. The presentation does not advocate for any particular position, but rather synthesizes and reports what the evidence shows. This content does not represent the views or positions of any institution, employer, or affiliated organization. This content is for educational and informational purposes only, and does not constitute legal, financial, medical, or other professional advice. No warranties, express or implied, are made regarding the accuracy, completeness, or reliability of the information presented. Use of this content is at your own discretion and risk. Thank you for engaging with this work. Let's begin. I agree with William Faulkner, but I think his statement requires more context because it is not the idea of the past, but the themes that live within the past that continually find their way back to the present. We can see how greed changes in how it looks while still producing the same outcome, which is inequity, until greed is eventually defeated through progressivism and effectively sealed away through policy reform like labor laws during the Gilded Age. It appears to me that we as a society continually fight the theme of greed, as greed represents the constant threat to equity and justice that our founding fathers sought to create through the Declaration of Independence in 1776. Perhaps equity and justice will one day be a reality for all men and women, once we work through every shape of greed there could be in existence and ensure that policies are in place to prevent that same shape of greed from ever reoccurring. Lastly, I think that this eternal battle truly represents and defines what the American experiment is, a morally persistent struggle against all odds, but more so being human greed in all its unknowingly infinite shapes. Paper Trail, Episode 2, The Pipeline. 1.18 million entities and the missing third. This episode is about how 2.1 million government documents get turned into searchable data, what the machine reads, what it misses, and how we know how much is still hiding. 1,178,767. That is how many named entities the pipeline has extracted from the corpus so far. Persons, organizations, locations, every name, every shell company, every city that appears in 2.1 million government documents. 432,000 persons, 670,000 organizations, 77,000 locations, each one extracted automatically from scanned pages, court filings, financial records, and correspondence. And that number is still growing. The pipeline has processed roughly 40% of the corpus. Named entity recognition is still running. Every day, the count climbs. What you see here is a snapshot, not a final tally. But before we can talk about what these entities mean, we need to understand how the pipeline found them. That starts with a problem. The raw corpus is 2.1 million files. Many are scanned photocopies. They are pixels, not text. A computer cannot search a photocopy the way you search a web page. It sees an image, not words. Some documents are handwritten. Some are so degraded that a human would struggle to read them. Faded ink, smeared copies, pages that have been photocopied, faxed, photocopied again, and scanned into a system decades later. These documents span decades: bank records, court filings, shipping invoices, emails, flight logs, FBI reports, House Oversight Committee records, every type of document you can imagine, in every condition from pristine to nearly unreadable. Before any analysis can begin, every single document must be converted into structured, searchable data. That is the pipeline's job. 16 scripts, 8 processing stages, 1 goal: turn pixels into entities without introducing errors that could mislead an investigation. Let me show you how it works. This is the full pipeline: 16 scripts organized into 8 stages connected by dependency arrows. Each stage feeds the next. Think of it as an assembly line, but one where every station depends on the station before it. Named entity recognition. The process of finding names in text cannot run until the text extraction is complete. You have to read the document before you can find the names in it. The relationship graph cannot be built until entities are deduplicated. You cannot map connections between people if the same person appears under 5 different spellings. Domain-specific parsers, built to read bank records and shipping invoices, feed their results back into the entity table, adding structured records that general-purpose extraction missed. 29.5 million relationship pairs pass through this network, each one traceable from document to entity to connection. This is not a simple linear sequence. It is a dependency network. If one stage fails, everything downstream stops. Nothing proceeds until its inputs are verified. Let me walk you through it, stage by stage. Stage 1. Every file gets a record in the database. File name, file type, size, which of the 12 datasets it came from, where it lives on disk. 2,100,266 records. This is the master catalog, the index of what exists before any processing begins. Nothing can be analyzed until it is first cataloged. Think of it like a library card system. Before you can search for a book, someone has to write down that the book exists and where it sits on the shelf. That is what this script does for every file in the corpus. Stage 2. Optical Character Recognition, OCR. This is the technology that reads a scanned page and converts it into searchable text. The pipeline uses 2 scripts for this. One handles PDF files, the other handles images. Each page becomes a markdown transcript stored alongside its original file. The original scan is preserved. The transcript is the machine's best attempt at reading it. But OCR quality varies dramatically. A clean typed letter transcribes perfectly. A third-generation photocopy of a handwritten note may produce complete gibberish. The pipeline processes everything. It does not skip the hard documents, but it cannot guarantee that what it reads is what the page actually says. That gap between what is on the page and what the machine thinks is on the page is where errors are born. Here is the spectrum. On the left, a clean document. The pipeline reads it perfectly. Every word, every name, every number comes through intact. On the right, a degraded scan. The pipeline reads it, but what comes out is barely recognizable. Garbled characters, words split apart or fused together, names that no longer look like names. Most of the corpus falls somewhere in between these 2 extremes. The pipeline does not skip the hard documents. It processes everything. but the quality of what it extracts depends entirely on the quality of what it is given. A perfect algorithm cannot fix a terrible scan. Source check. This is a recurring segment you will see throughout the series. On the left, an original scanned document from the corpus. On the right, what the pipeline extracted from it. You can see exactly what the machine read and compare it against the source. Green highlights show where the extraction matches the original. Amber highlights show where the text diverges, where the scanner misread a character or a word. This is how you verify any automated analysis, not by trusting the output, by checking the work. Every claim in this series can be traced back to a specific document. Every number can be audited. If we say the pipeline found something, you can look at the original page and confirm it yourself. That transparency is not optional. It is the standard. Stage 3. Named Entity Recognition, or NER. This is the core of the pipeline. A language model called spaCy reads every transcript and identifies every person, every organization, and every location mentioned in every document. Think of it as a trained reader that scans text and highlights every name it recognizes. A person's name, a company name, a city, a country. Every one gets tagged and stored. The model runs on 8 parallel processors simultaneously. So far, it has extracted 1,178,767 entities from 857,000 documents, and processing is still ongoing. Not every document in the corpus has been read yet. On screen, you can see what this looks like. The model reads a passage and highlights every entity it finds. Persons in blue, organizations in green, locations in orange. Each highlight is a data point that feeds into every analysis that follows. This is the foundation of every finding in the series. Every network connection, every timeline, every pattern starts here. The pipeline classified each entity by type. Here is the breakdown. 432,000 persons. 670,000 organizations, 77,000 locations. Organizations outnumber people 1.55 to 1. Stop and think about that. In a typical document corpus, court filings, news articles, business records, people outnumber organizations. That is the normal pattern. When you read a court filing, you see more human names than company names. When you read a news article, the same is true. Names of human beings almost always appear more often than names of companies. In this corpus, the ratio is inverted. There are more organizations than people. Why? Because the machinery of concealment generates more names than the people it conceals. Every shell company creates a new name in the record. Every trust creates a new name. Every limited liability company, every offshore entity, every subsidiary, each one adds another organization to the count. Research into the corporate network has identified roughly 53 known corporate entities tied to a single individual. 53 companies, trusts, and LLCs, creating 53 names in the record, all connected to one person. Multiply that pattern across every individual in the network, and you begin to understand why organizations outnumber people. Organizations do not just outnumber people in this corpus, they obscure them. Stage 4. Deduplication. The same person can appear in the corpus in multiple ways, different spellings, capitalization differences, OCR errors where the scanner misread a letter, abbreviations. Take one example. Nadia Marcinkova appears 8 different ways in the corpus. On screen, you can see all 8. Some are legitimate variations, an abbreviated first initial, an all caps version. Some are OCR mistakes. The scanner read an I as an L, or dropped a letter entirely, but all 8 refer to the same person. The deduplication script identifies these variants and merges them into a single canonical entry. One person, one record, regardless of how many ways the scanner mangled the name. 57,080 duplicate entities have been removed so far, but perfect deduplication is impossible. Some entities are still overcounted. The same person listed twice under names too different for the algorithm to match. Some different people with similar names may have been incorrectly merged. This is a known limitation, and the error rate is documented. Stage 5. When 2 entities appear in the same document, they get a connection in the co-occurrence graph. If a person and an organization are mentioned on the same page, the pipeline draws a line between them. The more documents they share, the stronger the connection. 29.5 million unique relationship pairs. That is the scale of the network the pipeline has constructed. Every person linked to every organization and every location they appear alongside, weighted by how frequently they co-occur. At the same time, the pipeline maps when each entity is most active in the corpus. On the right, a temporal activity curve. Spikes show periods of high activity, when an entity appears in many documents at once. Valleys show periods of silence, when an entity disappears from the record. These 2 layers, who is connected to whom and when, form the backbone of every investigation that follows. The graph shows the network. The timeline shows when the network was active. Together, they reveal patterns that no single document could show on its own. For now, the pipeline is building the map. Later episodes will read it. Stage 7. When standard text extraction fails. Handwritten forms, degraded scans, complex layouts, a vision language model steps in. Think of it as a more advanced reader that looks at the document as an image rather than trying to decode individual characters. The model is called Qwen 2.5 VL7B, 7 billion parameters. It runs entirely on a local graphics card, an NVIDIA RTX 4070. No cloud processing, no internet connection required. No data leaves the machine. This matters because the corpus contains sensitive material, financial records, personal information, legal documents. None of it is uploaded to any external service. Everything is processed on local hardware. The VLM handles cases that conventional text extraction cannot, but it introduces its own class of errors that look different from OCR mistakes. That is Episode 3. Stage 8. Purpose-built parsers for specific document types. These are not general-purpose readers. Each one is built to understand one kind of document. FedEx shipping invoices. The parser extracted 2,894 individual shipment records: sender, recipient, destination, weight, tracking number, charges. Every package that was billed to accounts in this network. Deutsche Bank wire transfers. 745 clean records totaling $38.9 million in traceable fund movements. Dates, amounts, originators, beneficiaries, account references. Every wire that moved money through the banking system. flight log entries from handwritten passenger manifests, email headers with sender, recipient, timestamps, and thread reconstruction. Each parser understands the structure of its specific document type and extracts structured records that general-purpose text extraction would miss. But these domain parsers process specific document types. The single largest category of documents in the corpus, the parsers have not touched it yet. 863,000 emails. Dataset 9, 531,000 email PDFs. Dataset 11, 332,000 email PDFs. Combined, they form the largest single category of documents in the entire corpus, more than the bank records, more than the court filings, more than every other document type combined. Named entity recognition coverage, 0%. Not a single name has been extracted from any of them. Not one person, not one organization, not one location. The pipeline has processed bank records, flight logs, shipping invoices, court filings, FBI vault documents, House oversight records. But the largest collection of documents sits completely untouched. Think about what emails contain. Scheduling correspondence. Who is meeting whom and when? Travel bookings. Who is going where and with whom? Personal communications between people in the network, in their own words. 863,000 of those documents, and the pipeline has read none of them. This is the blind spot. Pipeline stage. Here is the full processing map. Everything lit up in color has been processed. Metadata ingestion, text extraction, entity recognition, all completed across datasets 1 through 8, 10, and 12. Everything dark has not been touched. Datasets 9 and 11. 863,000 emails sitting in the pipeline with zero processing. Look at the contrast. The pipeline's reach is visible, and so are its gaps. The question now is not what the pipeline has found. It is what happens when we account for everything it has not found. 857,000 documents processed through named entity recognition, 40.8% of the corpus, less than half. Entity counts are still climbing. Every batch of documents that completes processing adds more names, more organizations, more locations to the database. The trend line is still rising. There is no plateau in sight. But the question is not just how many entities we have found. The question is, how many are we missing? If the pipeline has read less than half the corpus, how many entities are hiding in the documents it has not reached yet? Is there a way to estimate that number without reading every single page? It turns out there is. The pipeline borrows a technique from an unexpected place, not from computer science, not from law enforcement, from ecology. A technique borrowed from ecology. When biologists survey a rainforest, they do not count every species. That would take a lifetime. Instead, they count how many species they saw once. Those are called singletons. And how many they saw twice. Those are called doubletons. From that ratio, they estimate how many species are in the forest that they never saw at all. If you keep finding new species every time you look, you know you have not looked hard enough. The math tells you how far you are from seeing everything. The technique is called CHAO1 Species Richness Estimation. It was published in 1984. It has been validated in ecology, epidemiology, and information science. We applied it to the corpus. 821,633 entities observed. Estimated total, 1,290,141. 468,508. That is the estimated number of entities the pipeline has not found yet. Nearly 500,000 names, organizations, and locations hiding in documents the pipeline has not fully read. The corpus is approximately 2/3 read. 1/3 is still missing. And the confidence interval is narrow. The estimate falls between 1,283,000 and 1,296,000. The math is not guessing. It is measuring what we cannot see. Here is how it works. The formula has 3 inputs and 1 output. Step 1. Count your singletons, entities that appear exactly once in the entire corpus. 197,945 names appear in a single document and nowhere else. Step 2. Count your doubletons, entities that appear exactly twice. 41,816 names appear in exactly 2 documents. Step 3. The ratio between singletons and doubletons tells you how many unseen entities remain. The logic is intuitive. If you keep finding new names every time you open a new document, you know there are more names you have not found yet. A high proportion of singletons, names that appear once and never again, signals that you have not sampled deeply enough. There are more names hiding in documents you have not read. The formula. Take the number of entities you have observed, add the number of singletons squared, divided by twice the number of doubletons. The math. 821,633 plus 197,945 squared, divided by 2 times 41,816, equals 1,290,141. That is not a guess. That is a statistical estimate with a narrow confidence interval. 197,945. That is how many entities appear exactly once in the entire corpus. 1 document, 1 mention, and then silence. 24.1%. Nearly 1 in 4 entities is a ghost, a name that surfaces once and vanishes. A name appears in a single document and is never mentioned again anywhere in 2.1 million files. Some of these are OCR errors, a garbled scan that generated a phantom name. The scanner misread a word and created an entity that does not exist. Some are aliases, the same person under a different identity, appearing once under a name the pipeline cannot connect to their other appearances. And the singleton rate is remarkably consistent, 23.6% for persons, 24.6% for organizations, 21.9% for locations. That consistency suggests a systematic source, OCR noise, not a problem unique to any one entity type. But some of these singletons are real people, real names, mentioned in 1 document, never followed up on, never mentioned again. The pipeline can count them. It cannot tell you which is which, not yet. Distinguishing OCR ghosts from real people who appeared once and vanished is one of the hardest problems in this entire analysis. The pipeline's coverage is uneven. Not every dataset has been read to the same depth. At the top, datasets 3, 4, 6, 7, and 12 are 96% or higher complete. The pipeline has found nearly every entity they contain. These datasets are saturated. Reading them again would yield almost nothing new. In the middle, dataset 10, the single largest collection in the corpus, is 57.4% complete. Hundreds of thousands of entities still waiting to be found. At the bottom, the FBI Vault, 8.6%. Datasets 1, 2, and 5, all in the single digits. These are deep wells that the pipeline has barely tapped. And then datasets 9 and 11, 0. 863,000 emails that have yielded nothing, not because they contain nothing, but because the pipeline has not reached them yet. One anomaly stands out. The flight logs show 100% processing coverage, but only 23.2% completeness. That paradox is the next revelation. The richest veins are the ones we have not mined. The flight logs, 100% coverage. The pipeline has processed every single page. Every flight log in the corpus has been through text extraction and entity recognition. 1,292 entities extracted. But the CHAO1 estimate says there should be approximately 5,500 total. Only 23.2% complete, despite 100% processing. How is that possible? How can the pipeline process every page and still miss 3/4 of the names? Handwritten logs, degraded ink, abbreviated names, pilots writing in shorthand at altitude. The entity recognition model ran on every page, but what it could read was limited by what the text extraction could decode from handwriting. Most passenger names in the handwritten logs are still unreadable. The pipeline saw every page. It could not read what was written on them. 1,140 of those 1,292 entities appear exactly once, an 88.2% singleton ratio. Nearly 9 out of 10 names appear once and never again. Now a caveat, and this caveat matters. When the singleton ratio is this extreme, the CHAO1 formula can overestimate. It assumes singletons indicate undersampling. But in flight logs, the cause is different. Handwritten names that the scanner could only partially decode produce unique garbled strings that each appear exactly once. The math interprets that as evidence of vast hidden diversity. The reality may be simpler. The same name mangled differently each time. The math suggests approximately 5,500. The confidence interval runs from roughly 4,800 to 6,500. The true number is likely lower than 5,500. But even the most conservative reading indicates the majority of flight log passengers remain unidentified. Error log, honest accounting. Singleton rates, persons, 23.6%. Organizations, 24.6%. Locations, 21.9%. Overall, 24.1%. The consistency across all three types, within 3 percentage points of each other, suggests a systematic source. OCR noise, not a problem with any one entity type. When every category shows the same error signature, you know the source is upstream of the categorization. NER corpus coverage, 20.7%. 434,000 documents out of 2.1 million have completed entity extraction with finalized output. 40.8% of documents have entered the NER pipeline. Two notes on those numbers. 20.7% is the CHAO1 denominator, documents with fully processed entity output. 40.8% counts documents that have entered the pipeline but may not have completed. The gap between them is the processing queue. Deduplication has removed 57,080 entities. Entity resolution has produced 519,234 distinct clusters. Known issues. OCR noise generates phantom entities. Imperfect deduplication means some entities are still overcounted or undercounted. VLM coverage is partial. Only degraded documents have been reprocessed. These issues are documented. They are not hidden. That is the point of this segment. Transparent science. Why entity counts are inflated and what we do about it. First, 1.18 million entities includes massive duplication that deduplication cannot fully resolve. The same person, mentioned in thousands of documents with degraded name variants, can appear dozens of times. Deduplication removed 57,000 entries, but imperfect matching means some duplicates remain, and some different people may have been incorrectly merged. Second, OCR noise generates phantom entities from garbled text. A scanner misreads a page and creates a name that does not exist. A smeared photocopy produces a string of characters that looks like a name but is not. These phantoms enter the database as real entities. Third, the 24% singleton rate means nearly 1 in 4 entities may be artifacts rather than real people, organizations, or places. That is a significant fraction of noise mixed in with real data. We disclose these limitations because any methodology that hides its weaknesses should not be trusted. If someone shows you a number and does not tell you how confident they are in it, that is not transparency. That is marketing. The pipeline's numbers are not perfect. They are documented, and that is the difference. 5 quality gates, checkpoints that the pipeline must pass before its output is trusted. Entity resolution accuracy. The pipeline must correctly match entities above 84% of the time. Network modularity. The relationship graph must have meaningful community structure above 0.3. Recall. The pipeline must find between 75 and 80% of entities that are actually present. CHAO1 completeness ratio. The estimate of total entities should be less than 1.5 times the number we have actually observed. If the math says there are too many entities we have not found, the pipeline is not done. That last one is currently at 1.57, above the threshold. It is in alert status. The pipeline knows it has not found enough. That is not a failure. That is the system doing its job, telling us we need to keep processing. If a pipeline stage fails a quality gate, its output is flagged and all downstream analysis is paused. The gates exist to prevent cascading errors. One bad stage does not get to pollute everything that comes after it. You do not build on a foundation you do not trust. What you can do. Ask methodology questions, not what did we find, how did we find it. That single shift in thinking changes everything. When any analysis claims to process large data sets, in journalism, in government, in research, ask, what model was used? What was the error rate? What percentage of the data was actually processed? How was the output validated? Those questions matter more than the headline numbers. The tools used in this pipeline are available to anyone. spaCy is free and open source. Postgres is free and open source. The Department of Justice documents are public record under Public Law 119-38. You do not need a security clearance. You do not need a law degree. You do not need expensive software. The barrier to verification is not access. It is not money. It is time and effort. Every number in this series has a source. Every claim has an evidence table. Every finding can be checked. If you think a number is wrong, you can look it up. If you think a method is flawed, you can test it yourself. Verify. Do not trust. 1.2 million entities and counting. But the math says 400,000 more are hiding in documents we have not fully read. 863,000 emails that no algorithm has touched. The largest document category in the corpus, completely dark. Flight logs where most passengers are still unreadable. Names written by hand that no machine can yet decode. The pipeline built to read this corpus has read 2/3 of it. 1/3 remains. But here is what matters. The pipeline does not just count, it documents. Every number has a source. Every limitation is disclosed. Every error rate is measured. That is not a weakness. That is the standard every analysis of this corpus should be held to. The next episode is about what happens when the pipeline makes mistakes. When OCR sees Poland in a blank form. When it sees Krakow in a bank statement header. 2 observations, both retracted. The pipeline hallucinates, and the hallucinations look like real findings. Next time on Paper Trail, Episode 3, Ghosts in the Machine, When Machines Hallucinate. The word Poland appeared in a document about a bank account, except the form was blank. The word Krakow appeared in a financial statement, except it was the header of every page. 2 observations, both retracted. The pipeline makes errors, and the errors look like real findings. That is next time. I agree with William Faulkner, but I think his statement requires more context because it is not the idea of the past, but the themes that live within the past that continually find their way back to the present. We can see how greed changes in how it looks while still producing the same outcome, which is inequity, until greed is eventually defeated through progressivism and effectively sealed away through policy reform like labor laws during the Gilded Age. It appears to me that we as a society continually fight the theme of greed, as greed represents the constant threat to equity and justice that our founding fathers sought to create through the Declaration of Independence in 1776. Perhaps equity and justice will one day be a reality for all men and women, once we work through every shape of greed there could be in existence and ensure that policies are in place to prevent that same shape of greed from ever reoccurring. Lastly, I think that this eternal battle truly represents and defines what the American experiment is, a morally persistent struggle against all odds, but more so being human greed in all its unknowingly infinite shapes.